There are two types of cosmic coincidences: the kind that make you curious and the kind that make you uneasy. December 2025 delivered the second type. Within hours of the most intense solar activity in recent memory, 3I Atlas, an interstellar object millions of miles away, changed its behavior completely. Not gradually, not predictably. Abruptly, as if responding to a trigger. It began emitting a massive sunward jet, wobbling on its axis, behaving less like a dying comet, and more like a system under stress, trying to protect itself. Avi Loeb is asking questions. Stefan Burns documented the solar trigger, and the pattern emerging is too structured to ignore. We're about to walk through why this might be the most unsettling astronomical event of our generation. Stay until the end. The implications are worth it. Subscribe and stick around as we unravel this step by step, observation by observation. 3I Atlas is still out there, still moving toward Jupiter, still defying the patterns we built our models around. New data drops every day, and when the pieces finally lock into place, you'll want to be here. The answer is coming. Make sure you're here when it arrives. Something happened in late December of 2025 that shouldn't have happened. Not this fast, not this cleanly, and certainly not with this kind of timing. The Hubble Space Telescope released new images of 3I Atlas, the interstellar visitor currently passing through our solar system. Scientists expected to see what they'd been tracking for months: a comet-like object expelling gas and dust as it approached the sun, the kind of behavior we've documented thousands of times. What they got instead was something else entirely. The object had changed. Not gradually, not predictably, but suddenly and dramatically, as if someone had flipped a switch. For months, 3I Atlas had been venting material in a pattern that made sense. The jets were roughly symmetric, spraying outward from multiple points on the nucleus, like water from a lawn sprinkler. This is standard cometary behavior. Ice sublimits, gas escapes, dust follows. It's messy, chaotic, and beautifully random. But the new images showed something different. One dominant jet had emerged, highly focused and unnaturally collimated, pointing directly toward the sun. Let me be clear about why this matters. When a comet approaches the sun, it typically vents material away from the heat source. That's just physics. The sun heats one side, ice turns to gas, pressure builds, and material escapes along the path of least resistance, which is usually perpendicular to the sunward face, or away from it entirely. You don't see comets regularly blasting material straight into the teeth of solar radiation pressure. It's energetically inefficient. It's like trying to spit into a hurricane. Yet here was 3I Atlas, doing exactly that. The sunward jet wasn't subtle. It wasn't a minor adjustment in outgassing patterns. It was a reconfiguration, a complete change in how and where the object was expelling material. The brightness asymmetry was obvious even in processed images. One side of the object was significantly more active than the other, and that active side was facing the sun. But there was more. The object appeared to be wobbling. Not the gentle, predictable rotation you'd expect from a tumbling chunk of ice and rock, but something that looked almost like precession, as if the rotation axis itself was shifting. This hadn't been clearly detected before. The earlier observations showed rotation, sure, but nothing like this. Nothing that suggested the object's orientation was actively changing in response to something. Scientists have a term for what they were seeing: a mode switch. This wasn't just more activity, an increase in outgassing as the object got closer to the sun. This was a fundamental change in behavior. The object had been operating in one configuration, and then suddenly, within a span of hours to days, it had shifted into another configuration entirely. Now, comets can have outbursts. They can suddenly brighten or change their dust production. But those events usually build or have precursors. You see increasing activity, then a peak, then a decline, What happened with 3I Atlas looked different. It looked threshold-based, as if some condition had been met, and the object had responded accordingly. And then there was the timing. Because this mode switch, this sudden emergence of a sunward jet and apparent rotational wobble, didn't happen in isolation. It happened within hours to days of one of the most intense periods of solar activity in recent memory. The sun had just unleashed what space weather experts were calling a quadruple flare sequence. Multiple significant solar flares firing in rapid succession, flooding the inner solar system with high-energy plasma and charged particles. The temporal correlation was tight, tighter than most documented comet outbursts that might be linked to solar events. This wasn't a vague, around-the-same-time situation. This was clustered, stacked, uncomfortably close. Coincidence doesn't automatically mean causation. We know this. Scientists know this. But when two unusual events happen in extremely close temporal proximity, you pay attention. You ask questions. You don't immediately dismiss it because it's inconvenient or because it doesn't fit the models you've been using. Here's the thing about interstellar objects. They're not like solar system comets. They didn't form here. They don't have the same history, the same composition, the same structural properties. We're used to studying objects that have been shaped by 4.6 billion years in our specific neighborhood. 3I Atlas came from somewhere else. It carries information from another system, another set of conditions, and we have absolutely no idea what we're looking at beneath that dusty coma. So when an object like this suddenly changes its behavior right after the solar system gets hammered by plasma, you have to ask, why? Why would a chunk of ice and rock from interstellar space suddenly start pushing material directly toward the sun, just as high-energy particles are flooding through the heliosphere? What mechanism could explain that timing? The standard model says comets outgas when they get hot. Solar radiation sublimates ice. Pressure builds. Jets form. Simple. Predictable. But that model assumes the object is responding only to radiative heating. It doesn't account for charged particle interactions. It doesn't account for electromagnetic effects. It doesn't account for plasma bombardment altering surface chemistry or triggering subsurface volatiles in unexpected ways. And it definitely doesn't account for the possibility that we're not just watching passive physics. That maybe, just maybe, what looks like a comet breaking apart is actually something responding to its environment in a way we haven't seen before. The question isn't whether this is aliens. The question is simpler and more unsettling. Why would an interstellar object suddenly push material toward the sun right after the solar system was flooded with high-energy plasma? To understand why the timing matters, we have to talk about the solar event almost no one is connecting to this object. The sun tried to tell us something in December of 2025, and most of us weren't listening. Or more accurately, most of us didn't understand what we were hearing. Space weather forecasters track solar activity the way meteorologists track hurricanes. They watch for sunspots, monitor magnetic field configurations, and issue warnings when conditions suggest a major event. But even they were surprised by what happened. Not just one large flare, but multiple significant flares occurring in rapid succession, a stacked sequence that some observers started calling the quadruple flare event. Let me clarify something immediately. This isn't an official solar flare classification. You won't find quadruple flare in any textbook. What happened was that several substantial solar eruptions fired off within a compressed time frame, each one injecting enormous amounts of electromagnetic radiation and charged particles into space. The sun essentially coughed 4 times in a row, and each cough sent a wave of plasma screaming outward into the heliosphere. Solar flares are bursts of electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. They're powered by magnetic reconnection events, when twisted magnetic field lines suddenly snap and release their stored energy. But flares don't travel alone. They're often accompanied by coronal mass ejections, massive clouds of plasma and magnetic field that can take anywhere from 12 to 72 hours to reach Earth, depending on their speed and trajectory. What made this sequence unusual wasn't necessarily the raw intensity of any single flare. Individual flares are classified by their X-ray brightness, and while these were significant, we've seen larger ones. What mattered was the timing. When you stack multiple disturbances close together, the heliosphere doesn't have time to settle between events. The first wave passes through, compressing and heating the ambient solar wind. Then, the second wave arrives while everything's still disturbed, then the third, then the fourth. Imagine standing in a pool and someone makes a wave. The wave hits you, rocks you back, and then settles. Now imagine they make 4 waves in rapid succession before the first one even finishes passing. That's what happened to the inner solar system. Stefan Burns, who analyzes space weather data and shares his findings publicly, was among the first to highlight the unusual characteristics of this sequence. He focused on plasma density, particle anisotropy, and directionality. These are technical terms, but they matter. Plasma density tells you how many charged particles are moving through space. Anisotropy tells you whether those particles are flowing in one coherent direction or scattered randomly. Directionality tells you where they're going. Burns wasn't claiming aliens. He wasn't even claiming anything particularly exotic. He was pointing out that the conditions were unusual and that small bodies in the solar system might respond to those conditions in unexpected ways. This is the kind of analysis that usually gets filed away in technical reports and forgotten. But given what happened next with 3I Atlas, his timing looks prescient. To understand why this matters, you need to understand something called the heliospheric current sheet. This is a warped, undulating surface carried outward by the solar wind, where the magnetic field changes polarity. It's not a physical barrier, but it's electrically significant. Charged particles interact with it. Plasma flows along it or across it depending on conditions. And when you have a complex rotating structure like this getting hit by multiple coronal mass ejections in quick succession, things get chaotic. Small bodies like asteroids and comets interact with this plasma environment in ways we're still trying to fully understand. They can accumulate electric charge on their surfaces. They can generate temporary magnetic effects through the interaction of solar wind particles with their outgassing. If there are conductors or semiconductors in the nucleus, you can get interesting electromagnetic responses. Most comet models don't account for this level of detail. They assume steady-state solar conditions. The sun is treated as a constant heat source with a constant wind. But that's not reality. Reality is turbulent, variable, and full of transient events that get averaged out in the models because they're too hard to predict and too computationally expensive to simulate in detail. For solar system comets, this simplification might be acceptable. We've observed them for centuries. We have a decent baseline for their behavior. But interstellar objects are different. They have unknown composition, unknown structural integrity, and absolutely no prior conditioning by our sun. They're showing up already formed, already structured, and we have no idea how they'll respond to the specific plasma environment of our heliosphere. This is where things get uncomfortable. What if 3I Atlas isn't acting independently, driven purely by sublimation and thermal stress? What if it's responding to an external trigger, a sudden change in the charged particle environment that it encountered for the first time in who knows how many millennia? If solar events can provoke rapid behavioral changes in interstellar objects, then what we're watching might not be a comet passively decaying under solar heating. It might be something reactive, something designed or evolved or structured in a way that allows it to respond to environmental conditions we don't normally think about. And that brings us to the people quietly pointing out patterns they can't fully explain. Avi Loeb has a reputation. Depending on who you ask, He's either one of the most innovative thinkers in astrophysics or a scientist who's too willing to speculate beyond the data. He's the former chair of Harvard's astronomy department. He's published hundreds of peer-reviewed papers, and he's also the guy who suggested that Oumuamua, the first confirmed interstellar visitor, might have been an alien probe. This makes him controversial. It also makes him worth listening to, because Loeb asks questions that other scientists think, but rarely say out loud. And in December of 2025, he published an analysis of 3I Atlas that most people skim past without fully grasping what he was implying. Loeb focused on the rotation axis alignment. According to his analysis of the December observations, 3I Atlas appeared to be drifting toward an orientation where its rotation axis was becoming more aligned with the sun. This isn't something you expect from random tumbling. When an object is just spinning freely through space, knocked around by outgassing jets and thermal forces, it doesn't systematically reorient itself. It might wobble, it might precess slightly, but you don't get clean alignment with an external reference frame without some kind of sustained torque. He also discussed the jet wobble periodicity. The dominant sunward jet wasn't just there. It was apparently varying in intensity or direction with a regularity that didn't match the chaotic nucleus rotation you'd expect from a fragmented comet. This suggested something more structured was happening, either inside the nucleus or in how material was being released. Then there was the energy budget problem. Sustained, focused jets require ongoing energy input. Ice sublimation can provide that, but there's a limit. Once you've vented the volatiles near the surface, you need heat to propagate inward, to reach deeper reservoirs. That takes time. The speed and intensity of the change Loeb was analyzing seemed to require more energy than simple radiative heating could easily explain, especially given the object's distance from the sun at that time. Loeb didn't claim this was alien technology. He never does, not directly. What he does is highlight anomalies and point out when the standard model requires too many patches. He frames it as scientific curiosity, which is exactly what it is. But the subtext is clear. We're watching something that doesn't fit neatly into the boxes we've built. Consider the rotation axis alignment for a moment. If you have a symmetric comet nucleus tumbling through space, venting gas from random spots as different patches of ice get heated, you don't expect that tumbling to organize itself into a particular orientation relative to the sun. The forces are too irregular, too stochastic. But if you have an object with internal structure, with a mass distribution that isn't uniform, or with jets that fire in specific directions at specific times, you can generate torques that change the rotation state. This is orbital mechanics meets engineering. Natural processes can produce aligned rotation, but it usually requires very specific conditions. Tidal locking, for instance, where one face of a body always points toward the object it orbits. But 3I Atlas isn't orbiting anything in a way that would produce tidal locking on the timescale we're observing. It's passing through on a hyperbolic trajectory. The wobble periodicity is perhaps even stranger. Loeb's analysis suggested that the variations in the sunward jet weren't random. They had structure, a rhythm that repeated. That's hard to square with a nucleus that's breaking apart randomly or venting from newly exposed patches of ice in unpredictable ways. It suggests something inside the object is controlling or at least influencing the timing of the releases. Now, you can construct natural explanations for this. Maybe there are active regions on the surface that get heated in a cycle as the nucleus rotates. Maybe there are subsurface cavities that build pressure and release it periodically, like a geyser. These are plausible mechanisms, and they should be the first thing we consider. But here's where Loeb gets uncomfortable for the mainstream. The more natural patches you add to make the model work, the less simple the explanation becomes. Occam's razor, the principle that says you should prefer the simplest explanation, starts to cut the other way. At some point, you have to ask whether one exotic hypothesis is actually simpler than a stack of strained natural explanations that each require fine-tuning to match the data. Loeb doesn't push this argument all the way. He leaves it hanging, lets other scientists and the public draw their own conclusions. That's deliberate. He knows that if he says, "This might be technology," he'll be dismissed immediately by most of his colleagues. So instead, he says, "This is anomalous and worth tracking," and lets the implications speak for themselves. The response curve is another concept that keeps coming up in these discussions. Natural processes usually scale gradually. You heat ice. It sublimates slowly at first, then faster as more surface area is exposed. You spin up a nucleus with outgassing torques. It changes rotation states smoothly over many cycles. But the change observed in 3I Atlas looks threshold-based, as if some condition was met, and the object switched modes abruptly. Thresholds exist in nature. Water freezes at 0 degrees Celsius. Certain chemical reactions only proceed above specific temperatures or pressures. But the kind of threshold behavior that produces rapid, coordinated changes usually requires systems with feedback mechanisms, with internal coupling between different processes. You start stacking these observations, and you realize why Loeb's analysis is unsettling. Alignment toward the sun, periodic variations, rapid mode switching, sustained energy output. Each one individually has potential natural explanations, but all of them together in one object at the same time, right after a major solar event, the coincidences multiply. Loeb's genius is that he doesn't force a conclusion. He presents the data, he highlights the oddities, and he lets the pattern speak for itself. But the pattern is saying something uncomfortable. This object is behaving in a way that looks organized, not random, not chaotic, organized. And that raises a question nobody wants to ask out loud. What if the behavior isn't propulsion at all, but protection? Let me be absolutely clear before we go any further. What I'm about to describe is speculation. It's informed speculation, grounded in known physics and observable phenomena, but it's still hypothesis rather than evidence. The reason we're discussing it isn't because it's proven, but because it's plausible enough to warrant consideration, and because dismissing it without examination is just as unscientific as accepting it uncritically. The idea is simple. What if the sunward jet isn't about thrust or propulsion, but about creating a protective plasma envelope? This might sound like science fiction, but the physics involved are well understood. We know that charged particles interact with magnetic fields and with other plasma flows. We know that you can alter the trajectory of incoming solar wind by creating your own outflow of ionized material. We've observed this around planets, around comets, and around spacecraft. Venus, for example, has no magnetic field of its own, but it generates an induced magnetosphere through the interaction of the solar wind with its upper atmosphere. Mars once had a magnetic field, lost it, and now has a weak induced magnetosphere from solar wind interaction with its remaining atmosphere. These aren't shields in the sci-fi sense of glowing force fields. They're regions where plasma dynamics redirect incoming particles. Comets do something similar on a smaller scale. Their coma, the cloud of gas and dust surrounding the nucleus, gets ionized by solar ultraviolet radiation. The solar wind can't penetrate this ionized region efficiently, so it flows around it, creating a bow shock. The nucleus itself sits in a relatively protected zone, shielded not by a solid barrier, but by the collective behavior of millions of charged particles. Now extend that concept. Imagine you wanted to protect something from intense particle bombardment during a solar storm. Solid shielding won't work. High-energy particles just punch through. Magnetic shielding could work if you have strong enough fields, but generating persistent magnetic fields requires either permanent magnets or active systems with power sources. But there's another option: directional outgassing. If you vent ionized material toward the source of incoming particles, you create a countercurrent. The two plasma flows interact, and if you get the density and velocity right, you can establish a region where the net particle flux is reduced. Not eliminated, but reduced. You're not blocking the solar wind, you're redirecting it, creating a wake where the intensity is lower. This is environmental control through fluid dynamics, except the fluid is plasma. And the interesting thing about plasma is that it's conductive. It carries electric charge and magnetic fields with it. So when you inject plasma into the solar wind, you're not just adding particles, you're potentially altering the local electromagnetic environment. Could a sunward jet do this? Could venting material directly toward the sun during a period of intense particle bombardment create a temporary protective zone around the nucleus? The answer is maybe. It depends on the composition of the outflow, the ionization state, the velocity, and the density. If 3I Atlas is venting primarily neutral gas and dust, the effect would be minimal. But if it's venting ionized material, or material that gets rapidly ionized by solar ultraviolet, then you could get interesting plasma interactions. The objection to this idea is obvious. Why would a comet do this? Comets don't have nervous systems. They don't sense threats and respond strategically. They're inert objects governed by physics, not intent. But here's the subtle part. Protection doesn't require decision-making if the protective response is built into the object's structure. Think of it like a self-sealing tire. You don't need to detect the puncture and decide to seal it. The sealant is already distributed throughout the tire, and the change in pressure automatically forces it into the hole. The response is mechanical, automatic, triggered by the environmental change. If 3I Atlas has internal structure, reservoirs of volatiles connected to the surface through channels or pores, and if those channels have geometries or compositions that respond to charged particle bombardment, you could get automatic venting when the particle flux exceeds a threshold. No intelligence required, just clever engineering baked into the physical structure billions of years ago. Human engineers have thought about similar concepts for radiation shielding in deep space. We've studied magnetic deflection systems, plasma shields, and even concepts for using spacecraft outgassing to create protective envelopes. None of this is operational yet, but the physics is sound. We know it can work in principle. So when people dismiss the shield hypothesis as sci-fi, what they're really dismissing is the implication that something designed this. They're not dismissing the physics. The physics is fine. What makes them uncomfortable is the possibility that we're looking at engineering, not nature. But here's the uncomfortable question. How do you tell the difference? If a natural process and an engineered process produce similar observable outcomes, what distinguishes them? Usually, we look for signs of complexity, of optimization, of adaptation to specific environmental conditions. We look for functionality that seems unnecessarily sophisticated for random processes to have produced. And when you look at 3I Atlas emitting a focused, sustained sunward jet immediately following a major solar storm, with apparent alignment and periodic variations, you have to admit, that looks functional. It looks like it's doing something specific in response to specific conditions. Maybe it's still just a comet, venting gas in a weird configuration because of some structural quirk we don't understand yet. Maybe the timing with the solar flares is pure coincidence, and we're pattern matching where no pattern exists. Maybe all of this will resolve into perfectly mundane explanations once we get better data. Or maybe nature can mimic engineering so perfectly that we can't tell them apart. Or maybe, just maybe, engineering can hide inside nature, camouflaged by our assumptions about what's possible and what's probable. So why doesn't NASA talk about any of this? There is no cover-up. Let me state that explicitly before we go any further, because people love conspiracy theories, and this is exactly the kind of topic that spawns them. NASA isn't hiding evidence of alien technology. They're not suppressing data or silencing scientists. What's happening is more subtle and, in some ways, more problematic. The models we use to interpret astronomical observations are built on assumptions that make certain possibilities invisible. Comet models are phenomenally successful at predicting and explaining the behavior of solar system comets. They're based on decades of observations, spacecraft missions, and theoretical work. We know how ice sublimates under solar heating. We know how dust gets entrained in gas flows. We know how rotation affects jet patterns and how outgassing creates non-gravitational forces that alter orbits. These models work because they're built on a solid foundation of physics and calibrated against real data. But here's the catch. That calibration is specific to solar system comets. Objects that formed in the protoplanetary disk around our sun 4.6 billion years ago. Objects that have spent their entire existence exposed to our specific radiation environment, our specific composition ratios, our specific thermal history. Interstellar objects are different. They come from elsewhere. They formed under different conditions, possibly with different composition ratios, different structural properties, different thermal histories. They're carrying information from other stellar systems, other formation environments, and we have absolutely no calibration data for how they should behave. This is a problem when you're trying to model them, because your models inherently trust what they've seen before. This is called Bayesian inference in statistical terms. You start with prior knowledge, and you update it based on new data. But if your priors are strongly biased towards solar system compositions and behaviors, and if your new data comes from an object that doesn't conform to those priors, your model will try to force-fit the data into familiar categories. Oumuamua is the perfect example of this. The first confirmed interstellar object detected in our solar system passed through in 2017. It showed non-gravitational acceleration, meaning its trajectory changed in ways that couldn't be explained by gravity alone. This is normal for comets. Outgassing provides thrust. But Oumuamua had no detectable coma, no visible outgassing. So scientists proposed alternative explanations. Maybe it was outgassing hydrogen, which is invisible. Maybe it was an unusually flat object being pushed by solar radiation pressure. Maybe it was a fragment of a Pluto-like planet with exotic ices. Each explanation had problems. Hydrogen outgassing requires specific compositions and thermal properties. The flat object hypothesis requires an extreme shape we've never seen in nature. The nitrogen iceberg idea requires a formation environment we don't fully understand. Multiple competing explanations, none of them fully satisfying, all of them strained in some way to avoid the one explanation that fits the data perfectly, but violates our assumptions about natural objects, that Oumuamua was manufactured. NASA and the broader astronomical community aren't blind. They see these anomalies. But anomalies get treated as noise until proven otherwise. They get smoothed, averaged, fitted into the nearest acceptable category. This isn't malice or incompetence. It's how science protects itself from being overwhelmed by every odd measurement or unusual signal. The problem is that this filtering process is optimized to prevent false positives. We don't want to claim discovery every time a sensor glitches or a model misfits slightly. We want high confidence before we make extraordinary claims. But in being so careful to avoid false positives, we necessarily increase our rate of false negatives. We miss real signals because we've set the threshold too high, or because the signal doesn't look like what we've been trained to recognize. This is institutional inertia in action. Missions are designed years in advance with specific science goals based on established models. Instruments are optimized to detect expected phenomena. Data analysis pipelines are tuned to extract known types of information. If something unexpected shows up, it might not even register in the automated processing. It might get flagged as anomalous and set aside for later investigation that never happens because everyone's too busy with the primary mission objectives. There's also risk aversion to consider. Extraordinary claims require extraordinary evidence, which is a good principle. but it also means that even credible hints of something unusual get downplayed unless the evidence is overwhelming. Scientists are cautious about suggesting exotic explanations because it damages their reputation if they're wrong. They'd rather miss a discovery than be associated with a false alarm. This creates a paradox. If you never look for certain types of signals, you never find them. And if your models aren't designed to accommodate certain possibilities, those possibilities remain forever invisible to your analysis. Interstellar objects are challenging this system because they don't fit neatly into our existing boxes. They're edge cases that stress test our assumptions. And when those assumptions start breaking, when objects behave in ways that require multiple strained explanations to force them into the standard model, it's worth asking whether we're missing something fundamental. The system isn't blind. It's narrowly focused. It's optimized for studying what we expect to find, not for discovering what we haven't imagined. And 3i Atlas, with its sudden mode switch, its sunward jet, its coincidental timing with a major solar storm, is exactly the kind of edge case that should make us question whether our focus is too narrow. But 3i Atlas isn't the only place where the universe is acting structured. While everyone was focused on 3i Atlas and trying to figure out what was happening with its jets, another story was quietly developing in exoplanet research. The James Webb Space Telescope, humanity's most powerful infrared observatory, was returning atmospheric data from distant worlds, and some of those results were making chemists and planetary scientists uncomfortable. JWST was designed to analyze exoplanet atmospheres by capturing the light that passes through them during transits. When a planet crosses in front of its star from our perspective, some of the starlight filters through the atmosphere, and different molecules absorb light at specific wavelengths. By measuring which wavelengths are missing, we can determine what chemicals are present in that atmosphere. This technique has been revolutionary. We've detected water vapor, methane, carbon dioxide, and other molecules on dozens of exoplanets. But we've also started detecting chemical signatures that shouldn't be there, at least not according to our models of planetary atmospheres and chemistry. Several exoplanets have shown evidence of molecules appearing in combinations or concentrations that are thermodynamically unstable. They should react and disappear within relatively short timescales unless something is continuously producing them. On Earth, we have a similar situation with oxygen. Our atmosphere is 21% oxygen, which is wildly out of equilibrium. Oxygen is reactive. It should bind with other elements and disappear. The only reason we have so much is that photosynthetic life continuously produces it. The exoplanets showing these anomalies aren't habitable. They're hot Jupiters, gas giants orbiting extremely close to their stars, roasted to temperatures where complex chemistry becomes difficult. Yet, they're showing molecular signatures that suggest active, ongoing chemistry of a type we don't fully understand. One possibility is that we're seeing exotic atmospheric dynamics, convection patterns, or photochemical processes driven by the intense stellar radiation that can maintain non-equilibrium chemistry. Another possibility is that our models of high-temperature atmospheric chemistry are incomplete, and these molecules are more stable than we thought under extreme conditions. But there's also a third possibility that nobody wants to say out loud. What if some of these signatures are indicators of processes we haven't considered because we've only studied one example of a planet with an atmosphere maintained by biological activity? This isn't a claim that these exoplanets host life. They're too hot, too irradiated, too hostile for any biology we can imagine. But it's a reminder that chemistry in the universe might be more diverse and more active than our Earth-based models assume. We might be missing entire categories of processes because we've only sampled one planet in detail. The specific molecules causing concern vary from planet to planet, but several cases stand out. One hot Jupiter showed spectral features consistent with phosphine, a molecule that on Earth is primarily produced by biological processes or industrial chemistry. At the temperatures this planet experiences, phosphine shouldn't persist for more than hours or days. Yet there it is, apparently stable or continuously replenished. Another world showed evidence of methane and oxygen coexisting in the same atmosphere. On Earth, this combination is a biosignature, because these molecules react with each other. The fact that we see both simultaneously on Earth is evidence that something is producing them faster than they can destroy each other. Finding this combination on an uninhabitable world doesn't mean life, but it does mean chemistry we don't understand. The scientific community's response has been measured. Papers carefully phrase their findings as unexpected spectral features requiring further investigation, rather than anomalous chemistry that challenges our models. This is appropriate caution. New instruments sometimes have calibration issues. Data processing can introduce artifacts. Atmospheric models might need refinement rather than replacement, but underneath the careful language, there's genuine puzzlement. Multiple independent research teams analyzing different planets are seeing similar patterns of chemical disequilibrium. These aren't isolated measurement errors. They're systematic findings across multiple targets, multiple observation campaigns, multiple analysis pipelines. The pattern that's emerging across multiple domains of astronomy is similar. Systems behaving coherently, showing structure or organization or activity that requires explanations more sophisticated than random thermal noise or passive physical processes. Compare this with 3i Atlas. Different domain, completely unrelated phenomena, but the same underlying challenge. Observations that don't quite fit the models, that require either multiple strained natural explanations or one exotic explanation that makes us uncomfortable. Think about what it means to observe structure and coherence in places we expected randomness. A comet changing its jet pattern in apparent response to solar activity. A planet maintaining unstable chemistry despite conditions that should destroy it. These aren't just data points that fall slightly outside expected ranges. These are behaviors that suggest coupling, feedback, active processes maintaining non-equilibrium states. In physics and chemistry, maintaining a non-equilibrium state requires energy input. A hot cup of coffee cools to room temperature unless you keep adding heat. A chemical reaction reaches equilibrium and stops unless you keep supplying reactants or removing products. The natural tendency of all systems is toward maximum entropy, toward randomness and uniformity. When you see a system that resists this tendency, that maintains organization or structure or activity over time, you know something is driving it. On Earth, that something is often life. Biology is fundamentally about maintaining non-equilibrium states, keeping your internal chemistry different from your surroundings, harvesting energy from the environment to fight entropy. But life isn't the only possibility. Geological processes can maintain disequilibrium. Volcanism pumps gases into atmospheres. Plate tectonics recycles materials. Tidal heating keeps moons active long after they should have frozen solid. The universe has many ways to maintain structure without invoking biology. The question is whether our catalog of these mechanisms is complete, or whether we're about to discover that the universe is more creative than we imagined. Astronomy is shifting from static snapshots to dynamic events. We're no longer just cataloging what's out there. We're watching things change, respond, evolve. And the more we watch, the more we realize how much we don't understand about how systems behave on short timescales, how they respond to environmental triggers, how they maintain organization in the face of entropy. The old astronomy was like taking photographs. You'd point your telescope at an object, collect light for hours, or nights, or weeks, and produce an image. That image told you what was there, but not what it was doing. Modern astronomy is more like filming. We're watching objects over time, catching them in the act of changing, seeing how they respond to their environments. This shift reveals complexity we couldn't see before. A planet that looks stable in a single snapshot might show dramatic atmospheric changes when observed over multiple transits. A comet that appears ordinary in one image might be in the middle of a rapid transformation that only becomes apparent when you compare observations separated by days or hours. 3I Atlas emits a sunward jet after a solar storm. An exoplanet maintains unstable chemistry in a hostile environment. Oumuamua accelerates without visible outgassing. These are different problems, different objects, different physical processes, but they share a common theme. They're all challenging our assumptions about what's natural and what's not, about where the boundary is between passive physics and active systems. The word active is doing a lot of work in that sentence. In astronomy, we usually reserve it for objects with obvious energy sources. Active galactic nuclei have supermassive black holes. Active stars have convection and magnetic fields. But we're starting to see activity in places we thought were passive. Small bodies responding to their environments. Planetary atmospheres maintaining chemistry that shouldn't persist. Systems that look organized rather than random. This doesn't necessarily mean intelligence or design. Nature is capable of extraordinary complexity without anyone planning it. Evolution produces organisms of stunning sophistication through blind algorithmic processes. Self-organization creates structure in systems from weather patterns to galaxy formation without requiring a designer. But it does mean that our intuitions about what's natural might need updating. We tend to assume that natural equals simple, that complexity requires explanation, that structure requires a builder. But maybe natural processes can produce things that look designed, that behave coherently, that respond adaptively to their environments, all without any intent or purpose behind them. Or maybe, sometimes, what looks designed actually is designed, and we need better criteria for distinguishing between natural complexity and engineered complexity. The universe feels less passive than it did a few years ago, more reactive, more structured. Whether that's because the universe actually changed, or because our instruments finally got good enough to see what was always there, is an open question. Probably the latter. The universe didn't suddenly become more interesting in the past decade. We just finally built instruments sensitive enough and stable enough to watch it closely. JWST can detect molecules in alien atmospheres. Hubble can track small objects in real time. Our detector networks can catch transient events that previous generations of astronomers would have missed completely. Every time we improve our instruments, we discover new phenomena. Radio astronomy revealed pulsars and quasars. X-ray astronomy found neutron stars and black holes. Gravitational wave astronomy opened a window on colliding compact objects. Each new capability shows us things we didn't know existed, things that challenge our theories, things that force us to expand our understanding of what's possible. What's undeniable is that astronomy is entering an uncomfortable phase where the old models are under strain. Not broken, not wrong, but insufficient. They explain most of what we see, but the edge cases are piling up. The anomalies are getting harder to dismiss. And eventually, you have to ask whether the problem is with the data or with the framework you're using to interpret it. Science progresses through exactly this kind of discomfort. When observations don't match theory, something has to give. Usually it's the theory that gets modified, extended, or replaced. But sometimes it's our interpretation of the observations that needs updating. Sometimes we're measuring the right things, but asking the wrong questions. The accumulation of anomalies across different fields suggests we might be approaching one of those pivotal moments where multiple frameworks need revision simultaneously. Not because they're wrong, but because they're incomplete. They were built to explain phenomena within certain ranges, and we're now observing outside those ranges. So, what question are we really avoiding? This entire discussion, all 7 parts, has been circling around a question that nobody wants to ask directly. It's not, Are aliens real? Or is 3i Atlas a spaceship? Those are easy questions, binary, comfortable in their clarity. The real question is more subtle and more unsettling. What happens when reality updates faster than theory? We've built an extraordinary edifice of scientific knowledge over the past few centuries. We understand the laws of physics, the chemistry of matter, the evolution of stars and planets. We can predict eclipses centuries in advance and detect gravitational waves from colliding black holes billions of light years away. Our models work. They work phenomenally well for the vast majority of phenomena we observe. But models are approximations. They're built on assumptions, calibrated against specific datasets, optimized for particular types of problems. And when you encounter something outside the training set, something that violates the implicit assumptions baked into your framework, your models don't just fail gracefully. They actively mislead you, fitting the anomalous data into the wrong categories, generating plausible sounding explanations that satisfy the mathematics, but miss the physics. 3i Atlas might be a perfect example of this. Every piece of its behavior has a potential natural explanation if you consider it in isolation. Comets can have sunward jets under certain geometric configurations. Objects can change their rotation states due to outgassing torques. Brightness variations can result from changing active areas as the nucleus rotates. Solar events can trigger comet outbursts through various mechanisms. But when you stack all of these explanations together and insist that they all happen simultaneously in one object right after a major solar storm, you're not using Occam's razor anymore. You're using Occam's duct tape, holding together a model that wants to fall apart because it's being forced to explain something it wasn't designed for. Each individual explanation sounds reasonable in isolation. The sunward jet could be a geometric accident where the active region just happens to face the sun. The rotation change could be from asymmetric outgassing torques that happen to align just right. The timing with the solar event could be pure coincidence. Stack them all together, though, and you're asking for a remarkable convergence of unlikely events. This is where scientific reasoning gets tricky. We're taught to prefer simple explanations over complex ones, to avoid multiplying entities beyond necessity. But what counts as simple? A single exotic hypothesis or 5 strained natural explanations that all need to be true simultaneously? At some point, the cumulative improbability of the conventional explanation exceeds the initial improbability of the unconventional one. Correlation doesn't prove causation. This is statistics 101, and it's absolutely correct. Just because 2 events happen at the same time doesn't mean one caused the other. But here's the subtle part. Dismissing correlation can be as dangerous as accepting it uncritically. If you train yourself to ignore every coincidence, you become blind to actual causal relationships. You miss the signal because you're too busy protecting yourself from noise. Medical science learned this lesson through decades of epidemiological research. When people living near a chemical plant develop unusual cancer clusters, correlation doesn't prove the plant caused the cancers. But dismissing the correlation because it might be chance has repeatedly delayed recognition of genuine environmental hazards. The trick is to take correlation seriously as hypotheses worth investigating, while maintaining appropriate skepticism about jumping to conclusions. The same principle applies here. The correlation between the solar storm and 3i Atlas's behavioral change doesn't prove causation, but it does warrant serious investigation rather than automatic dismissal. It suggests we should be watching for similar patterns with future interstellar objects, looking for repeated correlations that would strengthen or weaken the hypothesis of environmental responsiveness. The scientific method is supposed to balance these risks. You propose hypotheses, you test them, you update your beliefs based on evidence. But when the hypothesis involves something outside your framework, something that would require revising fundamental assumptions about what's possible, the system resists. Not because scientists are closed-minded, but because extraordinary claims require extraordinary evidence, and the threshold for extraordinary keeps rising as the claim gets more exotic. This creates an asymmetry in how evidence is evaluated. Data supporting conventional explanations is accepted with relatively light scrutiny because it confirms existing frameworks. Data suggesting unconventional explanations faces intense skepticism and demands for certainty that may be impossible to achieve with current observational capabilities. The result is a conservative bias that protects against false positives but increases false negatives. There's a broader philosophical issue lurking here about the nature of scientific progress. We like to think science advances smoothly, with new evidence gradually refining our theories. But historically, major paradigm shifts have been messy, contentious affairs, where anomalies pile up for years before someone finally proposes a framework that makes sense of them all at once. Plate tectonics, quantum mechanics, heliocentrism, all of these faced initial resistance, not because the evidence was weak, but because accepting them required abandoning cherished assumptions. So we end up in a situation where multiple anomalies get individually explained away, each one receiving a plausible but strained natural interpretation, and nobody steps back to ask whether the pattern across all of them might be telling us something we're missing. Interstellar objects are messengers. They carry information from other parts of the galaxy, other stellar systems, other formation environments. Everyone that passes through our solar system is an opportunity to learn something about conditions elsewhere. But to learn from them, we have to be willing to see what they're actually showing us, not what we expect them to show us. Think about what interstellar objects represent. These are samples from stellar systems, dozens, hundreds, possibly thousands of light years away. They've traveled through the galaxy for millions or billions of years, exposed to radiation environments and gravitational interactions we can only guess at. They might have formed around stars with different compositions, different luminosities, different planetary system architectures. They're natural probes telling us about galactic diversity if we know how to read them. But reading them requires setting aside our parochial assumptions based on solar system objects. It requires entertaining the possibility that comet-like objects from other systems might behave differently than ours, not because they're artificial, but simply because they formed under different conditions and have different compositions and structures. Future detections should watch for specific signatures. Timing with solar events is one. If interstellar objects repeatedly show behavioral changes correlated with space weather, that's a pattern worth investigating, regardless of what it implies. Alignment shifts are another. If an object's rotation state changes systematically rather than randomly, that tells us something about its internal structure or its response mechanisms. Threshold responses, where behavior changes abruptly rather than gradually, suggest systems with feedback or switching mechanisms. We need a systematic catalog of interstellar object behaviors. Right now, we have a sample size of 3: Oumuamua, Borisov, and 3I Atlas. That's not enough to establish patterns or distinguish typical from anomalous. We need dozens, hundreds of detections before we can say with confidence what normal interstellar object behavior looks like and what constitutes a genuine anomaly. The Vera Rubin Observatory, scheduled to begin full operations soon, will help enormously with this. Its wide-field survey capability should detect multiple interstellar visitors per year. Within a decade, we'll have statistically meaningful samples. We'll be able to ask questions like, how many show evidence of outgassing? How many change brightness unexpectedly? How many correlate with solar activity? How many show alignment or rotation anomalies? We should also start thinking seriously about what I'll call cosmic weather. The idea that interstellar space isn't empty, isn't static, but filled with fields and particles and radiation that vary on timescales from seconds to mega years. objects traveling through this environment might be shaped by it, adapted to it, responsive to it, in ways we haven't considered because we've only studied objects that have always been in our local neighborhood. The galaxy isn't a vacuum. It's threaded with magnetic fields, filled with low-density plasma, pervaded by cosmic rays and background radiation. Objects traveling between stars are swimming through this medium for millions of years. They're being slowly eroded by interstellar dust impacts, irradiated by galactic cosmic rays, charged by interactions with the interstellar medium. By the time they arrive here, they might be very different from when they left their home system. This extended exposure to the interstellar environment might produce structures or properties we don't see in solar system objects. Surface chemistry altered by cosmic ray bombardment. Internal damage from radiation over geological timescales. Even erosion patterns that depend on the object's trajectory through different galactic environments. These effects might make interstellar objects systematically different from their solar system cousins in ways we're only beginning to consider. The possibility that we're already immersed in larger systems, that the galaxy is more interconnected and more dynamic than our models assume, isn't comfortable. It means we're not as isolated as we thought. It means that events happening in other parts of the galaxy might have consequences here. It means the universe is watching us just as much as we're watching it. This isn't mysticism or anthropomorphism. It's recognition that our solar system exists within a larger context. We orbit within the Milky Way's disk, exposed to whatever radiation and particles flow through our neighborhood. Nearby, supernovae might have triggered ice ages on Earth. Encounters with giant molecular clouds might perturb the Oort cloud and send comets raining into the inner solar system. We're not separate from the galaxy. We're embedded in it, subject to its influences. Uncertainty is a feature, not a flaw. Science thrives on uncertainty because it drives investigation. When we're uncertain, we ask better questions. We design better experiments. We challenge our assumptions. The worst thing we can do is pretend we have answers when we don't, or dismiss observations that don't fit our current framework simply because they're inconvenient. Embracing uncertainty doesn't mean abandoning rigor or accepting wild speculation. It means being honest about the limits of our knowledge and maintaining openness to possibilities we haven't fully explored. It means holding our conclusions tentatively while gathering more data rather than committing prematurely to explanations that might be wrong. 3I Atlas is still out there, moving through our solar system, venting material, changing its behavior in ways we're still trying to understand. Whether it's a comet breaking apart under stress or something more sophisticated is ultimately an empirical question. But the answer matters less than the process of honestly engaging with the data, acknowledging what we know and what we don't, and being willing to consider possibilities that make us uncomfortable. Because here's what we can say with confidence. Something didn't just pass through our solar system. Something interacted with it. The jets changed. The timing correlated with a solar event. The behavior showed structure and apparent responsiveness. These are facts, observations, measurements made by our best instruments and analyzed by credible scientists. What those facts mean is still open. What they imply about the nature of interstellar objects, about the diversity of phenomena in the galaxy, about the boundary between natural and artificial, between passive and active, between random and organized. Those are questions we're only beginning to ask. And maybe that's the real point. Not to have answers, but to recognize when we've encountered something that demands new questions. To acknowledge when our frameworks are insufficient and our assumptions are showing cracks. To remain curious and humble in the face of a universe that keeps surprising us. 3I Atlas will eventually leave our solar system, fading back into the darkness between stars. But the questions it raises will remain, and the next interstellar visitor might not be as subtle. The next correlation might be too obvious to dismiss. The next anomaly might finally force us to revise our assumptions about what's possible and what's natural. Until then, we watch, we measure, we debate, and we try very hard not to let our models blind us to what's actually there. Something came through our solar system, and something changed. Whether that change is a comet dying or a system activating is a question we may not be ready to answer. But we can't afford to stop asking it,